Let's look at a more complicated counting problem where we have more than one restriction of an and or on our set. So we're given the set C, and we're asked how many subsets of C have a 3 or an A or a 7. So what this really means is because we have the or, we're really saying how many subsets have at least one of these 3 elements in them. So for example, if you have the subsets that for sure have an A fixed in them, we would definitely want to count those. If we're looking at the subsets that definitely have a 3 in them, well, they at least meet the criteria of having the 3, so we do want to count those. Similarly for 7. Similarly for A and 3, it has at least one of these 3 in them, so we want to include the subsets that have those as well. Subsets that have an A and a 7, subsets that have a 3 and a 7, and of course the subsets that include all 3 of our elements that we want to count. And finally, if we're looking at subsets that have neither an A or a 3 or a 7, we do not want to count those subsets. So how are we going to do this? As always, I'm going to use both methods. I'm going to use first the 2 to the power of n method, and then I will try and compute this with our n choose k method. So let's go ahead and do that. All right, so for our 2 to the power of n method, let's recognize that all of these categories of sets we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different types of categories of subsets. These categories encompass every possible subset of C. So overall, this is the total number of subsets of C that you can have. So it's going to be 2 to the power of n, or 2 to the power of 5, since we can choose 5 of these. So that's going to be 32 total subsets of C. Now, what do we want to do? Well, because there's 8 categories here and 7 of them are what we want to count, that's going to be a lot of subsets to count. So maybe it'll be easier to simply take the total and subtract simply what we do not want, the subsets we don't want to count. And that's going to be this one category down here. And what does that one category include? Well, it simply includes the subsets that only include 90 and y, right? Neither of these, all the subsets that could be made out of these 2 elements do not include at least one of these 3, so they do not fit the subsets we want to count. So how many subsets can you make with just these 2 elements and nothing else? Well, you can just picture that this is our new subsetting, or our new set in question. And that's going to be 2 to the power of n, or 2 to the power of 2, right? We have 2 elements here, so it's going to be a 2. And there are 4 subsets that have a 90 and a y and do not include at least one of these 3. And of course, you could logically think about this. This would be the empty set, the set only including a 90, the set only including the y, and of course the subset including the 90 and the y, right? Every other subset is going to include one of these 3, so we just want to subtract from the total these 4 subsets, and we're going to be left with the number of subsets that have definitely one of these 3 in them. So we're going to end up saying the answer is going to be 2 to the power of 5, the total, minus 2 to the power of 2, what we do not want, which is going to be the same as saying 32 minus 4, which is going to be 28. So this means there are 28 subsets of C that have at least a 3 or a 5, a 3 or a A or a 7. Okay, so our second method is going to be a little bit more advanced, but nonetheless very, very good to know. Okay, so how do we interpret this diagram? Well, everything in this circle are going to be the subsets that have a 3 in them. So it's going to be all of these dots over here. All of the dots that are going to be in this circle down here are going to be all of the subsets that definitely have an A in them. So it's going to be all of these dots here. Next, we're going to have this circle represent all of the subsets that definitely have a 7 in them. Now, of course, I didn't draw all of the subsets in accurate dots. This is just like a visual representation. There's not enough dots here. There's supposed to be 28 given our previous solution, but I'm not going to draw 28 dots. But what do we notice here? Well, the technique we're going to try and do is we're going to first count all of the subsets that only have a 3 in them, or that definitely have a 3 in them. So we're going to count all of these. I'm going to circle in blue. Then we're going to count all of the subsets that definitely have an A in them. So it's going to be all the ones I circle here in red. And finally, we're going to count all of the subsets that definitely include a 7. I'm going to just highlight these in black. So what do we notice? Well, if we were to count all of the subsets with blue, it'll be 1, 2, 3, 4, 5, 6, 7, 8. Then if we count all of the subsets that definitely have an 8, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. And if we count all the subsets that definitely have a 7, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. But what's the issue here? How many actual dots did I draw for my subsets? It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have a total of 19 circles drawn. But because we've counted 3 that have 8, the number of subsets that definitely have a 3, the number of subsets that definitely have an A, and the number of subsets that definitely have a 7, if we add up all of these, it's going to be 8 plus 8 plus 8, which is going to be 24. So we've counted 5 extra subsets than we should have, which doesn't make sense. There's only 19 dots. Why did we end up counting 24? Well, it's because of the dots that have been circled more than once. As you notice here, when we counted all of the subsets that have a 3, we would have included one of these dots, especially the dots, for example, that would have been in this category here. These would have included the subsets that have 3 and A, and then the ones that we counted down here would have included the set that has A and 3. So we've clearly counted a set like this, for example, twice, and we don't want to do that. So how are we going to resolve this issue? Well, we're going to simply subtract after counting all of the subsets that definitely have one of these elements. We're going to subtract from this the sets that have both of them. So we're going to subtract from this, because this has been double counted. This includes the subsets that have both of them, right? We're going to subtract it once. So we're going to subtract from this just the subsets that have 3 and A once, because we've counted those twice. Similarly for 7 and A, we're going to subtract the sets that have both 7 and A once. So this is going to be minus the subsets that have 7 and A. And then finally, we're going to also subtract all the subsets that have both a 3 and a 7, right? We're going to get rid of one of these rings. There we go. So it's going to be 3, 7. Fantastic. But what do we notice at the end? Well, we've now gotten everything to be counted once, except for this middle one down here. This middle one down here no longer is circled because we've gotten rid of all 3 of the rings that were around it. So what are we going to do? Well, clearly we've now no longer counted. We're going to be at least 1 off. And what does this area represent? This represents the subsets that have all 3 of those elements. So at the end, we're going to just want to add all of the possible subsets that have all 3 of our elements. And this should, in fact, after we draw this additional circle here, mean that we've counted every single subset in each category that fit our question only once. So let's go ahead and do that. Okay, so firstly, how are we going to compute this? Well, this is simply going to be n choose k. Okay, so let's start by counting all of the subsets that definitely have a 3 in them. So we're going to be fixing the 3. What does this mean? Well, in our n choose k notation, n represents how many things you can choose. Well, you can't choose the 3 anymore. We're saying it definitely has to be in these subsets. So you can only choose out of the remaining 4 elements. So our n becomes a 4. Then our k, this is where you have to really think about it. Well, you can say to the subsets including definitely a 3, you can add none of them. Sorry, right? You can add none of the elements out of the 4. So this would just include, for example, the subset containing only 3, right? Or we'll add a plus sign here. We can say out of the 4 you can add 1, or out of the 4 you can add 2, or out of the 4 you can add 3, or out of the 4 we can add all 4 elements, right? Each of these would be, for example, this would be including subsets that have, for example, a 3, and let's say y, right? That would be adding 1. Adding 2 with this, right, this up here would be something like 7. Adding 3 would be something like adding a third element like 90. And then adding all of them would just be writing down all of them here, right? So how many ways can we do all of these options? Well, there's only going to be one way you can add nothing to this subset already including a 3. So that's going to be 1 plus, there's only 4 ways you can add 4 elements once to a subset already including 3. So that's going to be 4 plus, well in this case we're going to have to compute this notation, which is going to be 4 factorial over 2 factorial multiplied by 4 minus 2 all factorial, which is just going to be 4 times 2 to, 4 times 3 times 2 times 1 over 2 times 1 multiplied by 2 factorial, because 4 minus 2 is 2, so that's going to be 2 factorial, which is just going to end up being times 2 times 1. What do we notice? The 1's cancel, the 2's cancel, so we're left with 4 times 3, which is 12, over 2 times 1, which is 2, so 12 over 2, that's going to be 6. There are 6 ways you can add to a subset already having a 3, 2 more elements to that subset, so plus 6, plus, well this is going to be a similar story, we're going to have to compute this very quickly, 4 minus 3 factorial. 4 minus 3 is 1, 1 factorial is 1, so we're not really going to look at that. 4 factorial over 3 factorial is just going to be 4 times 3 times 2 times 1 over 3 times 2 times 1, which is just going to be 4, right? Because the 1's cancel, the 2's cancel, the 3's cancel, you're really just left with a 4. So there's only going to be 4 ways you can add 3 elements to a subset already including 3. So it's going to be 4 plus 1, because there's only one way you can add all 4. Fantastic. So this is going to be 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus 1 is 16. There we go. So there are 16 subsets that definitely have a 3 in them. Now we're going to want to do this similarly for A and 7. What do we notice? Well, that's going to be the exact same problem we just computed, but instead of fixing the 3, we're going to instead now fix an A, and we're going to get the exact same sort of numbers here. So that's just going to be another 16. There's 16 subsets that definitely have an A. Similarly, for 7, we're just going to fix the 7. And we notice we have 4 options, 4 at the top. And then we're going to say we can add 0, 1, 2, 3, or all of them, right? And you're going to, again, get 16. So we've already computed the top up here to just be 16 plus 16 plus 16. Now we need to subtract from all of these, this sum, we're going to need to subtract this second row down here. So we're going to want to compute now how many subsets have a 3 and an A. So let's go ahead and do that. So now what we're going to be doing is, because we're now going to be looking at the number of subsets that definitely have 2 elements, we're going to be fixing 2 of them. So let's take 3 and A. We're going to fix the elements 3 and A. So what this means is we only can choose from 3 remaining elements to be in our subsets we're going to be counting. So that's going to mean our n becomes 3. And we can say, okay, you can add none of the elements to a subset that contains 3 and A. You can add 1 of them, 2 of them, and of course you can add all of them. So now all that's left really is for us to compute these. Well, there's only one way to add nothing. That's going to be plus 1. There's 3 ways to add one of those 3 remaining elements to a subset already containing 3 and A. So that's going to be plus 3. Okay, now we need to compute 3 factorial over 2 factorial times 3 minus 2 all factorial. This just becomes 1 factorial, so we're going to ignore that. 3 factorial is 3 times 2 times 1 over 2 factorial, which is 2 times 1. The 1's cancel, the 2's cancel, you're really just left with a 3. So there are 3 ways to add to any of these 3 elements, any 2 of those 3 remaining elements to a subset already containing 3 and A. So that's going to equal to 3 plus 1. There's only one way you can add all of them, so we're going to get 8. Now notice the problem of 3 and A is what we just computed, but it's going to be the exact same number for 7 and A and 3 and 7, because you're just going to say, well, instead of fixing 3 and A, we're going to fix A and 7. Or instead of fixing A and 7, we're going to fix 3 and 7, right? The top is still going to be 3's, and we can still only choose 0, 1, 2, or 3 of them. So this really ends up being 3 times all of this, because we need to subtract all 3 of these possible groups that we have. So this is going to end up being 3 times 8. Or we're just going to write this down maybe a little more explicitly as 8 plus 8 plus 8. Fantastic. Finally, what's the very last thing we want to do? Well, doing this and then subtracting from the sum of this, we're going to end up not including... Holy fuck, you scared me.
I'm sorry, I was trying to cry.
Jesus Christ. You were so silent. I just saw like eyes. Hi. Jesus. Holy shit.
I was trying to be quiet.
You were very quiet. You were a ninja. Holy moly. Okay.
Are you okay?
Yeah, you scared me. I was so focused. Oh, okay. I love you. Okay, anyways. So now that we've excluded, unfortunately, all of the subsets that include all 3 of them, we're going to have to count them. Because obviously, though the subsets that include all 3 are subsets that fit our criteria. So how are we going to do that? Well, now we're simply going to ask ourselves the n choose k method, and this time we're going to fix all 3 of them because the subsets we're counting have to have all 3 of those elements. So how many elements can we really choose from now? Well, it's going to be 2, so our n is going to become 2. And what can we say? Well, we can choose none of the remaining 2. We can choose one of the remaining 2, or we can choose all of the remaining 2, which is going to be 2 choose 2. So how are we going to compute this? Well, we know we can only choose nothing once. You can only choose one of 2 twice. And you can choose all 2 only once. So this is going to end up being 4. So there we go. We've now computed all of these different categories that we need for our final answer. So let's go ahead and get our sum. Our sum is going to be 16 plus 16 plus 16 minus 8 minus 8 minus 8 plus 4. So what are we going to get? We're going to get, this is going to equal to 8 plus 8 plus 8 plus 4, which is going to be 16 plus 12, which is going to be 28, which is exactly the answer we got with our first method.